Hi, and welcome back to Mechanical Systems Design. In this video, we'll discuss analyzing different modes of failure. And we'll have some exercises, so bring a piece of paper and a pencil and a partner so you can get the most out of it. So what do I mean by failure? Failure means that my mechanical system no longer works well enough for my purposes. And this can happen lots of different ways. Parts can yield, where they plastically deform and don't return to the original shape. They can fracture, break into pieces. That can happen from exceeding the ultimate strength of the material, or fatigue strength if you have cyclic loading, or buckling, an unstable deflection that leads to very high stresses and breakage. Or the system can fail simply by elastically deforming too much for your application. And this is just a few common ways. There are many others like surface wear and so on. Yield and fracture are probably the most familiar to us at this point, and we've been applying these already. And what you do is you compare the yield strength or ultimate strength of the material to the maximum stress you expect your component to experience. You get those strengths from a chart specific to the material, and you get your strength from back of the envelope analysis or finite element analysis. And here's a classic video of a material test on a benchtop. The force is gradually increased until it yields. You can see a plastic deforming here. It won't pop back to its original shape, and then fractures. And the yield strength is just the force at which it starts to neck divided by the cross-sectional area. And the ultimate strength is the force at which it breaks into pieces divided by the original unaffected cross-sectional area. Now, fatigue is very similar, except it happens after lots of cycles. And so a component might be able to take a load one time, but it can't take that same load 100 million times without breaking. And so when we compare our maximum strength, in this case, we'll compare it to the fatigue strength, which will depend not only on the material, importantly, but also on the number of cycles. And generally, the more cycles we will load the part, the lower the fatigue strength. And of course, it's also modified by some other factors, as we discussed in the topic reading, like the surface finish, the size of features, and so on. And here's a classic example of fatigue failure. This part is being cyclically loaded at a high frequency, and a crack has initiated on the top edge, then slowly propagated over maybe millions of cycles, and then eventually the remaining material just isn't enough to take the load and it fractures. And this happens even in systems in our laboratory. These are a pair of ankle exoskeletons that have this, we call it a heel spur, sticking out behind the heel. And there's a rope that pulls up, and every step it pulls up to assist the person as they walk, so cyclic loading. And we made this component using 3D printing of titanium, which is cool because it lets you make these complicated swoopy shapes with hollow interiors, but it introduces some things that make you more subject to fatigue. For example, in order to get the material out of the inside, that's like this sintered titanium, so you can get that weight savings of the thing being hollow, well, we need these holes to let the material out and actually chisel it out, really. And those introduce stress concentrations. And you can see that a crack initiated at the corners of this hole, and then propagated through, leading the part to fail. And another thing about 3D printed metals is that they tend to be anisotropic, and you can have asperities and voids, and that makes the material more likely to fatigue out as well. Another common failure mode is buckling. And buckling is best understood as an unstable deflection of a structure that's under compression. So let's say we have a column here, and a little gust of wind nudges it just a tiny bit so that this point is no longer straight above this reaction point on the ground. Well, it now is a moment that can tend to cause the structure to bend, but also the structure has some stiffness, and it will try to spring back into place. If the springiness outweighs the moment due to the displacement of the load, then it won't buckle and it's stable. But if the moment due to that little tiny displacement is bigger than the springiness moment to put it back into place, then it will deflect more and the moment will get bigger. And the springiness will also get bigger, but not as fast. And so you have this rapid acceleration, and big deformations that tend to result in big stresses and things breaking. Now, when we analyze parts for buckling, we'll compare this critical force, that's the force at which the applied load starts to beat out the springiness of the structure. And we'll compare that to the applied load we expect in our application. You can estimate this by hand using a classic formula here, where we have the critical force being about equal to a constant times pi squared times the elastic modulus. That's important because it tells us how springy the material is, times the area moment of inertia of the cross section divided by length squared. And length squared appears in the denominator because that has something to do with how much a little deflection will increase the leverage of our force at the top. In more complicated buckling modes, we can analyze those using finite element analysis. Now, one of the most important decisions we'll make when we set up any buckling problem, whether it be by hand or in FEA, is how we constrain the component's deformation. And on the left here, we have a case where we're saying both the ends are pinned, so they can rotate freely, but this can only translate straight up and down, and this can't translate at all. And that corresponds to this constant value of 1 for our critical force. Now, if we fix the angles of the endpoints as well, you can see that the shape of our deformed column gets more curvy. And so for the same moment of that applied force, we get much bigger springiness, springy force, popping it back into place. And so we get this higher constant. Oops. Here, a constant value 4. So a 4 times higher critical load. And similarly, if we fix one end, but allow the other end to move side to side, which is a big difference from our first case, then now you can see the curvature is much more slight. And there's less springiness tending to bring it back into place. And so our critical force is smaller. And you can, of course, do this for many different modes. Now, buckling is something that we see in the laboratory as well. And here is an example from a full leg exoskeleton where applying a test where we're stepping up a very large force, 250 Newton meters of knee extension, and something breaks. And you can see it happening in here. There's a big tension force here at the end of this beam, which is essentially beam and bending. So the top part is under tension and the bottom of the beam is under compression. And that bottom part under compression buckles. And the way it buckles is out of plane. It's very common buckling mode in thin structures. So if you look at the carbon fiber from the side, it's like this, but end on it's like this. And so the way it's buckled is to pop out and then overlap. And you can kind of see that happening right here. All right, a final failure mode to look out for is excessive deflection or stretching, where we simply calculate the expected deflection, compare it to what's allowable for application. And you can do this by hand for lots of classic loading scenarios like an axial prismatic member. We just have the force times the length divided by the cross-sectional area times the elastic modulus. For a cantilever beam, the endpoint deflection is just the force times the length cubed divided by 3 times the elastic modulus times the area moment of inertia of the cross-section. And for a tube or anything else under torsion, we have the torque times the length divided by the polar moment of inertia of the cross-section times the shear modulus, which is another material property very similar to the elastic modulus. And if we have a complex system with weird deformations, we can calculate those in finite element analysis. There are lots of examples of things bending a little too much, lots of great bridge videos. The Millennium Bridge is one of my favorites because it turns out that the reason it deforms so much is because movement of the bridge caused people to take steps synchronously with other people on the bridge, which a colleague of mine demonstrated. Okay, so now let's do some exercises to apply at least one of these new failure modes, and we'll return to our vice grip. So the first thing to do is perform a buckling analysis of link 1. So what I'd like you to do is get out a pencil and piece of paper, draw a free body diagram, write down your critical force equation for link 1. And do that on your own first, then compare answers with your partner and come back. And that should take, maybe 3 or 4 minutes, all right? So hit pause now. All right. So probably during that process, you noticed you had to make up some parameter names and so on. Now what we'd like to do is invert the analysis and solve for one of those geometric parameters. So think about which of the part geometry aspects you think you'd like to use this analysis to exactly meet your factor of safety, and then do that algebraic manipulation. All right, this should also take 3 or 4 minutes. So hit pause now, and then we'll come back and discuss results. All right, sounds easy, right? But then there are lots of tricky little decisions for us to make. So let's take a look. The way we can start this problem is by drawing the free body diagram. And as we discussed in our FBD's lecture, this turns out to be a two-force member. So we have these two forces, collinear, equal and opposite. And this is a kind of long, kind of skinny thing. So classic case where we'd be worried about buckling. And we're going to have to define this length. We know that'll show up in our buckling equations. And we'll have to define something about the cross section. Let's say it's rectangular with a thickness and height. And then we get to the big tough decision, which is what is the mode of buckling that we're most concerned about and therefore that we model. And a lot of people looking at this problem will think, okay, I'm looking at this thing from the side. It's pinned on either end. I saw pinned in that table in the book. So let's say this is the buckling mode I'm interested in. And that's perfectly good. But we'll see that it probably will not be the limiting buckling mode. So in this case, we have this constant of 1 because it's pinned. We have the area moment of inertia that we care about will be the one about this centroid here. And so that'll be 1/12 thickness height cubed. Well, let's say we get to thinking, this looks like the thickness is a little smaller than the height. And I would, the area moment of inertia would be smaller if we calculated it about this centroid. And that's true. And that's the second case. So let's say we still assume pinned, but now we say it's instead of buckling like this in the plane that we were presented, it's buckling like this out of plane. And while I is going to be smaller, that will result in a smaller critical force. So that's more concerning. But then we start to think, well, pinned, that means that we're assuming that those endpoints are forced to exactly point at each other. And well, what is constraining that? I mean, we have the rest of the structure there, but it's not perfect, right? It's not going to exactly keep those things pointing. Maybe they can kind of pop off to the side a little bit. And we know from looking at our tables that would result in a lower curvature and a lower constant, and so a lower critical force. And it's going to turn out that that is probably the buckling mode we need to be most concerned about. So if we substitute these terms into our buckling critical force equation, we have that the critical force, we want that to equal our factor of safety times the expected force. And the critical force will be equal to pi squared times c times e times I divided by L squared. So if we substitute in for case 3, we get the factor of safety times the force is the critical force, and that's equal to pi squared e h t cubed over 48 L squared. Now we have this another decision, which is which of our geometric parameters do we want to try to solve for? So we could solve for the length, except that's kind of set by the geometry of this vice grip and how it's going to be used. We can't really make that thing super short, or we won't have the kind of range we want over which to grip the part. So that leaves us with the height and the thickness. Well, let's say that the height we think, oh, that's going to have something to do with, the diameter of these holes and so on. Plus the thickness has the most effect on the critical force for this type of buckling. So we can solve for thickness, and it's going to simply be equal to 48 over pi squared. So this is some constants that have to do with, the derivation of this critical force formula and of the area moment of inertia. The factor of safety times the force, bigger factor of safety, bigger thickness, that makes sense. 1 over the elastic modulus of the material, that makes sense also. The stiffer the material, the less likely it is to buckle. And so the less thickness you're going to need. Length squared, so longer, more prone to buckling, bigger thickness, that makes sense, divided by the height of that cross section. And of course, the taller it is, that will increase the area moment inertia and act to prevent buckling, making that spring stiffer. And then all that is to the 1/3 power. Okay, so that's how we do this using back of the envelope analysis. What about CAD? Well, let's take a look at link 1 in SolidWorks. All right, so here we have link 1 from our vice grip, which we've analyzed in some previous studies. This time we're going to create a new study and analyze it in buckling. So instead of static, which we used for stress, we'll come down to buckling and say, okay. And then the first thing to do is just the simplest darn thing we can think of and see what happens and go from there. So let's start by creating fixed geometry here in this one hole, and then applying a force at the other hole in a selected direction. We want it to go along the line of our part, and let's say 100 newtons. And note that the way we've set this up, that corresponds to the fixed free boundary conditions that we used in our hand analysis. So this FEA should be consistent with that. And we can run this study, and it should go pretty fast. And what we're going to get is 2 critical pieces of information. So first, we're going to see the deformed shape of the part. And if we kind of look at this from the side, we can see the qualitative shape is something like what we expected. We've got this part hasn't moved because it's fixed. This part has shifted off to the side in that classic fixed free buckling configuration. So that's the first thing to take a look at. The second thing is the quantitative result. And there's really only just one thing you care about in terms of the numbers here. All this stuff is kind of irrelevant. It's all relative. But this number up here is absolute, and that is your load factor. Here we have a load factor of 46. That means we applied a load of 100 newtons. We would need 46 times 100, or 4,600 newtons for this component to buckle. And this would be the shape it would pass through on its way to unstable deformation and fracture. So it would only instantaneously have this shape, but this isn't the deformed shape. This isn't the displacement. This is showing us qualitatively the way it deforms during that unstable deflection of buckling. So if we want a factor of safety, it's 46. Of course, there might be other ways that this thing could buckle. And in some cases, the first shape that we get won't be what we're interested in. So let's see some more modes. We'll go up to the top here, right click, properties, and we can ask for SolidWorks to find more buckling modes for us. If we say okay, we can rerun the study and take a look at different ways it could buckle. All right, that took just about 15 seconds. And so now if we right click on the chart and edit definition, we'll see that we can choose among different buckling modes. And if we go up from 1, we'll see that the load factor is increasing. So the factor of safety is getting bigger and bigger. That's one way to navigate this. Another way to navigate it is we have these little buttons down at the bottom of our chart, and we can select through different mode shapes. Okay, here's another one. And this looks kind of like that 4th mode shape in our table right, where it kind of goes through 3/4 of a sinusoid. And that corresponds to a higher load factor. So this won't happen in the real system because before it buckles with this shape, it will buckle with the simpler quarter sinusoid shape, right? And if we keep looking through these, we will find, aha, this looks quite a bit like that first shape that we considered, where instead of buckling out of the plane, it would buckle in the plane, right? Where we can see the curvature while we see the holes. And we'll note that that load factor is about 16 times higher than the other load factor, and that is consistent with the theory here. Okay, great. So that's how we perform buckling analysis for a relatively simple shape. What about something a little more complicated? By opening up the link to assembly from last week. All right, so let's say we're interested in understanding how something might buckle, taking into account the fact that there are other pieces of the structure that also provide springiness that might help pop it back into place if it gets a little deflection. Well, we can do that in an assembly analysis like this. So here we've used a very similar setup as we used to analyze the stress of this assembly. We've got this component up here is subject to a fixed hinge. We've got a fixed hinge down on this hole, and then we have a distributed force along this surface of link 2 to represent the force from the fingers. And we, unlike a stress analysis, we won't be able to do any global contact other than bonded or penetration, sort of a ghost mode where things can pass between each other. So it's not able to handle things pulling away in a no penetration fashion, but for our purposes, that's probably just fine. So we've got those two fixtures and our external force. We've got enough to run our simulation, and I've done that. So let's take a look at what we get. Okay, I ran 100 mode shapes, and the first one we see is pretty weird and ugly and doesn't look like something that's very likely to happen. So let's edit our definition, and we'll try to find a mode shape that we like. So mode shape 1 here corresponds to a load factor of negative 1,519. Now, negative load factor, that means that this is what would happen. This is how it would buckle if we applied the force in the opposite direction. But I'm not interested in anything that could happen if the fingers had glue on them and pulled away from link 2 really hard. So in this case, we really only care about positive load factors, but we can't ask SOLIDWORKS to restrict it to those. So instead, what I'm going to do is come up here and type 1, and you'll see that I'm getting a mode shape down there, and it's the nearest one to what's available. But you can see indeed mode shape 17 corresponds to a positive load factor, and 16 is negative. So let's go with 17 and see what that looks like. You can see here that what we have is out of plane buckling of link 2. The basic idea is that anytime there's a piece of the material that's under compression, buckling is possible. And when you have bending, well, this top portion of the material is under compression, and the bottom portion is under tension. And so you can have buckling. But it doesn't always kind of look like those shapes in the plane that we draw, because you can imagine it's a little easier for this thing to pop out if it bends a little as well, because the cross section is thinner than it is tall. So it's much wobblier and more flexible in that out of plane direction. And so we have compression, we have something that's skinnier than it is tall, and those two things lead to this out of plane buckling shape. Something definitely to look out for, as structures it tends to be the case that as a structure is more and more optimal for a particular type of failure mode, other failure modes become more important and eventually become dominant. All right, let's look at some of these nearby buckling modes. Oh, that's interesting. So here we have out of plane, but more like a 1.5 sinusoid for that second link. And we can see that in order for that to happen, links, both of the link one models in this part have to do a funny buckled shape where the tops are at the same angle, but they're offset, right? So that isn't quite captured by any of the simple models that we analyze using our hand analysis. And we'll see there's a whole bunch of these. I'm going to show you one more that's kind of interesting. So here is a buckling mode where you can see link 2 has not changed its shape much, and the link 1 has quite a lot. And this is closest to that fixed case where the ends were constrained to move exactly at each other, and the angles had to be held constant, but the middle part could bow out. And that's kind of what we're seeing here. Of course, all of this stuff corresponds to a higher load factor than the lowest positive load factor for mode shape 17 here. And so if this part, if the load were increased and increased, and we didn't exceed the yield strength or ultimate strength of the part, eventually this is what would happen. It would buckle with that handle popping out of plane. So that is how we analyze components for buckling, and an overview of some of the other ways we can analyze components for failure.